Hello, my name is Cody Freitag, and today I'll be talking about the impossibility of strong KDM security with auxiliary input. This is joint work with Ilan Komargodski and Rafael. To start off, I want to look at, before getting to the full notion we consider in this work, just the standard notion of public key encryption. So to start off with the syntax, first, any public key encryption scheme comes with a key generation algorithm that on input the security parameter outputs public key and secret key pair. Then the encryption algorithm takes the public key and a message M and outputs a ciphertext uh, for this message M. And then there's a decryption algorithm that on the secret key and a ciphertext for the message M decrypts it and gets back the message M. And the standard notion of security, we consider what's called semantic security, which stipulates that a ciphertext for a message which is 0 is indistinguishable from a ciphertext for the message which is just 1. So in other words, no polynomial time attacker can distinguish encryptions of 0 from encryptions of 1. And I want to point out that in this definition, actually we have to fix the messages first, and then we look at the probability over a random secret key and public key pair. And this is important because in particular, it doesn't capture the case where the messages themselves might depend on the keys. And this actually comes up in a lot of natural scenarios, like if you're doing some disk encryption, like Windows 10 BitLocker application, where you're encrypting the full hard drive, this will require you to actually encrypt the secret key that you used for the scheme. So this requires some guarantee, not only just for fixed messages, but also messages that might depend on the output of the key generation algorithm. Additionally, this sort of key-dependent property comes up in applications for fully homomorphic encryption. So for bootstrapping kind of smaller schemes into larger, fully functional homomorphic encryption schemes, we require some sort of security even when encrypting specific keys. And so this raises a additional notion of security to semantic security called circular security, where you generate a random secret key public key pair, and then you ask that in addition to semantic security holding, ciphertexts of a string of all zeros are indistinguishable from the ciphertext of the secret key. And here, by 0 to the s, I just mean padding sufficiently to be the same size as the secret key. So encryptions of the secret key are indistinguishable by polynomial time attackers to encryptions of just all zeros. And you can even push this further to what's called key-dependent message security, or KDM security, which again, you sample a secret key public key pair, and you consider any efficient function f and require that encryptions of an all zero string are indistinguishable from encryptions of this function f applied to a secret key. And here the key thing is that the messages are allowed to depend polynomially on the keys in some arbitrary way. In particular, since this allows for any efficient f, this also implies kind of normal semantic security if f is just independent of the secret key. So the question that gets raised is every semantically secure scheme also KDM secure? In other words, is there a reason that we're going through all of this kind of technicalities to define circular security, KDM security, or is it just like a natural definition that's satisfied by any semantically secure scheme? Turns out the answer to this question is no. And in particular, it's easy to show that there exists an encryption scheme such that first, semantic security holds. So encryptions of 0 and encryptions of 1 are indistinguishable by polynomial time attackers. But encryptions of the secret key can be easily distinguished from encryptions of the all zero string of the same length. And the counterexample is actually pretty straightforward. So all it relies on is the existence of some semantically secure encryption scheme. So in particular, I'm going to consider this algorithm enc star, an encryption scheme with this encryption algorithm that takes in a public key and a message, and it's either going to output just a ciphertext according to any semantically secure encryption scheme, called CT sub m, in the case that m is not equal to the secret key. But if it is equal to the secret key, then it's going to do the same, but also just release the secret key. And kind of intuitively, this should be easily easily distinguished in the case that the message is the secret key, because even the output just looks different. Whereas semantic security should still hold, because any person who's trying to kind of construct messages, you wouldn't be able to guess the secret key before it's been generated based on the definition of semantic security. And the key idea of why this is about counterexample is because actually testing whether a message is a secret key is easy. You can just see, does this message decrypt random messages that I generate encryptions for? And so this kind of gives a very straightforward way to show a semantically secure encryption scheme that's not KDM secure, at least not this kind of restricted circular secure definition. But this doesn't imply that every scheme doesn't satisfy KDM security. And in particular, one of the early works that kind of introduced this notion showed that you can construct KDM secure encryption schemes in the random oracle, where all the parties have access to kind of a common random function that will generate fresh randomness for you. And even more so, we have from various structured assumptions like decisional Diffie-Hellman, learning with errors, quadratic reciprocity, we have a line of works that can at least construct bounded KDM secure encryption schemes, meaning that the encryption scheme can support a class of functions, but it needs to itself depend on this class of functions. And in general, most natural schemes, they seem like they should be KDM secure. They're at least believed to be KDM secure. The counterexample I gave you before seemed very targeted and contrived in breaking this specific circular security notion. So maybe we can just conjecture that if a scheme isn't constructed in this contrived way like that, then it should be some sort of KDM secure. And so this gives us hope. It turns out KDM security is very useful in a lot of settings, so let's just kind of use it. And for now, we don't see any problems with many notions of KDM security. So I want to try to, in this work, push this a little further and consider a strengthening of this standard KDM security notion I put forth before, which I'll call strong KDM security with auxiliary input. And so I'll provide three strengthenings to the definition before. The first is that I want to consider the setting where the keys may be maliciously generated. So there's some possibly malicious distribution D that outputs a distribution of public keys. And we're going to consider only distributions where kind of semantic security holds. Encryptions of 0 and encryptions of 1 are indistinguishable. Additionally, I'm going to let the distribution output public auxiliary input. And I'm going to require that even with this public auxiliary input, still semantic security holds. And you can think this kind of auxiliary input is used in a setting where some adversary is generating their own public key, and this is inside some other protocol, so you need security to hold even within the context of some greater protocol. And now I want to say that given such a distribution, I'm going to say an encryption scheme satisfies KDM security if whenever this distribution satisfies normal semantic security, then this strong version of KDM security also holds. In particular, I'm going to say that the scheme satisfies this notion if when the distribution satisfies semantic security, then for any inefficient or exponential time function f, it's indistinguishable encryptions of all zeros versus encryptions of this function f applied to the public key and auxiliary inputs. So you can think this is like KDM security even for exponential time functions. And just to point out that this captures normal KDM security, because this is an exponential time function, it could even compute the secret key and then do a polynomial or even more expensive algorithm on the secret key. So we weren't the first to consider this notion. Actually, a work by Deshpande and Kalai in 2018 used this notion to construct two message witness hiding protocols, sort of weakening zero knowledge while doing it in fewer rounds. And I want to just point out that in isolation, none of these strengthenings to the standard KDM security themselves seem too harmful. Like, it's reasonable that, again, as long as the encryption scheme isn't contrived. Maybe there's a natural encryption scheme that can satisfy this requirement. And so what we ask in this work is, does there exist such a scheme? Is this a valid assumption to make or something to use in protocols and applications moving forward? And as you might be able to guess from the title of our talk, our main result is no. So in particular, assuming the learning with errors assumption and the existence of one-way permutations, we show that no semantically secure encryption scheme satisfies this strong KDM security with auxiliary input definition. And in fact, this result holds even in the case that the auxiliary input is very short, in particular, sublinear in the size of the public key. And for this kind of extended result, we additionally assume non-leveled, fully homomorphic encryption. So I want to, for the rest of the talk, give kind of an outline of the proof of our main result. So to do so, we have to take any secure encryption scheme given by a key generation, encryption, and decryption algorithm, and we need to construct a distribution D and a function F such that, on the one hand, this distribution and outputs public keys such that the auxiliary input in ciphertext of 0 is indistinguishable from the same auxiliary input in a ciphertext for 1. But at the same time, it actually is possible to distinguish ciphertexts of this function f on the public key and auxiliary input. It's able to distinguish this between ciphertext of the all 0 string. So this is what we need to show in this proof, and this is what we'll do. So towards this, I want to consider two main ingredients that we use. The first is a specific pseudo-random generator. This is a function g that on input some seed s outputs two values, y1 and y2. And we need the following two properties. First, the second output, y2, information theoretically determines y1. But at the same time, y1 is indistinguishable from random, even given y2. So computationally, it's kind of has high pseudo entropy, but at the same time, y2 fully determines y1. And in fact, such a PRG exists from kind of the standard construction of PRGs from a one-way permutation. The second ingredient we need is called compute and compare obfuscation. So this is where, just to first describe compute and compare functions, we have a compute and compare function CC, which is parameterized by an inner function f and a target u. And on input x, the compute and compare functionality either outputs 1 if the function f on input x outputs the target u, and outputs 0 otherwise. So it just computes the function f on the input, checks to see, does a comparison to check to see if it's equal to the target, and outputs 1 if so, and 0 otherwise. And then we need to be able to take this seemingly simple functionality and we need to be able to obfuscate it. So jumble up the code in the circuit in some way such that this obfuscated version can be simulated only given kind of the size of the function, the size of the target, and the security parameter, and not given the actual details of the function or the target itself. And such a scheme exists from the learning with errors assumption. And this was shown by these two works in 2017. Okay, so now that we have our ingredients, we're ready to describe the attack. So again, we're going to start with any encryption scheme, and we're going to consider distribution D that on input the security parameter first outputs, runs the PRG G on a random seed and gets two outputs, y1 and y2, and it also just generates, honestly, a secret key and public key pair. Next, it's going to construct this obfuscated circuit with the following property. So the function it uses is going to be the decryption circuit with the secret key hard-coded, and the target is going to be the first output of this PRG. So what does this mean? This means that this functionality on input, an encryption of y1 will output 1, since an encryption of y1 will decrypt to y1. However, given any other message as input, it'll output 0. So it's an obfuscated circuit that only outputs 1 on valid encryptions of y1. Okay, so the output of this distribution is just going to output the honestly sampled public key, and the auxiliary input consists of the second output of this PRG as well as the obfuscated circuit. Okay, so that's the distribution. Now let's define this function. So the function takes in the public key and the auxiliary input, all the public information. And what it's going to do, it's just going to output the value y1, which, recall, can be information theoretically determined by y2. And so what we're going to show is that, recall the outline of the proof, we have any secure encryption scheme, we've constructed this distribution D in a function f. So now we need to show semantic security holds, but kind of this strong KDM notion with respect to this function f does not hold. So this can be distinguished. So we'll start with part B here. So for part B, we want to show ciphertext for all 0 strings can be distinguished from ciphertext of this function in the presence of this auxiliary input. So recall the auxiliary input consists of this y2 value, the obfuscated circuit, the function on this public information just outputs this y1 value output by the PRG. And then the obfuscated circuit outputs 1 on encryptions of y1 and 0 otherwise. So let's consider the following distinguishing adversary. All it's going to do, it receives auxiliary input and a ciphertext as input. It's going to take the obfuscated circuit from the auxiliary input, run it on the ciphertext, and just output the result. So let's see why this distinguishes these two worlds, the left-hand side where you have an encryption of zeros and the right-hand side where you have an encryption of y1. So if the message is all zeros, then the decryption on a ciphertext of all zeros will just be all zeros, and this won't be equal to y1 with high probability because y1 was chosen randomly as the output of a PRG. So this implies that the obfuscated circuit will output 0, so the distinguishing adversary will also output 0. Okay, now let's consider the right-hand side, the world where the message is y1. So here, the decryption of a ciphertext for y1 is just y1, and so the obfuscated circuit will output 1, and so the adversary outputs 1. So this shows this adversary A can distinguish the world on the left versus the world on the right. So these are distinguishable. So part B is done. Next, we need to show A that semantic security still holds. Okay, so to do this, we're going to do it by a sequence of hybrids. So for our first hybrid, hybrid 0, we're going to look at the output of any distinguishing adversary A on auxiliary input and a ciphertext for 0 using the distribution D, where recall this is the distribution where PRG outputs 2 values, you sample the keys honestly, you construct this obfuscated circuit, and output the relevant information. So next, we're going to consider a hybrid where we switch the obfuscated circuit to the simulated version. And we're going to look at what is the adversary A's output now given this simulated distribution. And the point is that because the target of this obfuscated circuit has high pseudo entropy, even given y2, which is in the auxiliary input, then we can do this swap and the distribution of A's output won't change too much. And so finally, now that we have kind of the auxiliary input is just y2 and something that doesn't depend on the secret key at all, by standard semantic security, we can switch the ciphertext of 0 to a ciphertext of 1, and A's output won't change too much. And then finally, we can go back to the hybrid where A is just using the original distribution D via the same argument as before. So because each successive pair of these hybrids are indistinguishable, it says that the left-hand side, which is given by hybrid 0, is indistinguishable from the right-hand side, which is given by hybrid 3. So this establishes that semantic security holds with respect to this distribution in the presence of this auxiliary input, but for this function f, an adversary with this auxiliary input can easily distinguish ciphertext of zeros from a ciphertext of this function applied to this public key and the auxiliary input. Okay, but the auxiliary input here contains this like large obfuscated circuit, which is probably very complicated. So what if we change the definition to having the exact same thing, but requiring that the size of the auxiliary input is much smaller than the size of the public key? And in fact, the work by Despande and Kalai show in 2018 that even this kind of restricted form can be used for two-message witness hiding. Unfortunately, the answer is still no. And the key idea is that we can maliciously generate the secret key public key pair using a short seed. And so then I need to argue that given this observation, we can make the auxiliary input much shorter. So this follows from the fact that we can use the same idea to make y1 and y2 much shorter than the public key. And also, since the secret key can be generated using a short C, it has a compressed description. So we can also compress the description of the decryption circuit with that uses SK, and hence also the obfuscated circuit that's included in the auxiliary input. There's one subtlety here, which is that we actually require succinct compute and compare obfuscation to make sure things work out fine here, but it turns out that such an obfuscation exists from kind of non-leveled fully homomorphic encryption, which maybe a little ironically is secure based on kind of a circular security assumption, which recall is weaker than the strong notion we consider. So it is plausible that there exist encryption schemes, and therefore there with this circular security notion, and therefore it's plausible that there exists this non-leveled FHE scheme. Okay, so that's all I wanted to say about kind of the impossibility we show in this work, but I want to conclude with a few takeaways. So first, KDM security really can be useful in a lot of scenarios, either in a very practical sense of when you're doing like disk encryption or encrypting your hard drive, to a lot of other scenarios where you need this kind of bootstrapping technique like for fully homomorphic encryption, or even it was shown recently that it can be used possibly to construct indistinguishability obfuscation, one of the kind of holy grails in cryptography over the last many years. However, I want to point out that we still need to be careful when we're pushing it too far. It's good to kind of push the boundaries some, understand what's possible, what's not, but kind of I hope this work shows that in some settings, especially when in the presence of auxiliary input, you really need to be careful about what you're willing to assume. And lastly, I want to just emphasize that in many natural scenarios, kind of these attacks that involve kind of the presence of auxiliary input, where there might be some obfuscated circuit inside, in many of these, actually, we only need very weak forms of obfuscation or obfuscation for very simple functionalities in order to break security of this scheme. So I think this is a good example of just given this kind of simple compute and compare functionality, we can obfuscate that, kind of hide what's going on inside the code there. And this weaker form of obfuscation can be used to break security for a natural definition. So yeah, thank you for your time.